Hello, everyone. Oh, I think you got an echo. All right. Hello, everyone. My name is Mohammed. I'm a research engineer. And can you guys hear me? Yep. Okay. Yep. I'm a research engineer here at FAIR and a member of the Open Catalyst project. We have a pretty busy schedule, so I think we should just go ahead and get started as people start to trickle in. We're going to start off a quick agenda of what we have planned for today. You guys probably have already seen. We're going to start with a challenge overview, summary of the results, some analysis. We have two invited talks throughout the course of the session. We have Gabor Csányi and Yoshua Bengio, as well as talks from our runner-ups and our winners. And at the end, we do have some time for a discussion for people who have specific questions regarding the competition, general questions about the project in general, or anything else that comes to mind. So without any further ado, let's go ahead and get started with the challenge overview. So many of you have probably chatted with Abhishek, but Abhishek couldn't be here today, so he prepared a pre-recorded video that we'll go ahead and share. Let's go. All right.
Hi everyone, welcome to the Open Catalyst Challenge presentation. My name is Abhishek Das, and I'm going to provide a brief overview of this year's competition, including details of the task, the dataset, the results, and some analysis. I wanted to start off by acknowledging that the Open Catalyst project is a giant effort by FAIR at Meta AI and Carnegie Mellon University. This competition wouldn't really have been possible without the contributions of the entire team. The primary motivation of the Open Catalyst project is that in order to address climate change, we need to move towards renewable energy sources. To ground this, I'm showing a plot of energy demand versus renewable energy generation for a day in California. As you can see, there's quite a bit of a gap between energy demand and renewable energy generation. Now, if you were to naively scale up wind and solar farms, the plot might look something like this. During the day, when the sun's shining, there's excess generation. And then during the night, when the sun's not shining, there's excess demand that's unmet. So essentially, we need a way to store energy so that we can transfer it from times of peak generation to peak demand. Now, if you think of ways to store renewable energy, a couple of options pop up: batteries and pumping water uphill. Batteries are inherently limited by the material scarcity and cost. And pumping water uphill, although extremely efficient, is limited by the amount of mountain valleys available to flood. One option that has the potential to be scaled to a country or a global-sized grid is to use this excess electricity generated from renewable sources to convert it to storable forms. For example, we can use electricity to break down water into hydrogen and oxygen, store that hydrogen that can later be reused in fuel cells to convert back to energy. Alternatively, we can use this hydrogen along with carbon dioxide from the atmosphere to generate methane or ethanol that can later be used to generate energy. So essentially, our goal is to find high-performing catalysts that can drive these chemical reactions at high rates without being consumed in the process. So let's look at how these interactions with the catalyst play out in practice. Here, I'm showing an illustration of a system from our dataset. The large blue and gray atoms comprise the catalyst, and sitting on the catalyst surface is the adsorbate molecule. The system starts off in an initial high energy state. The atoms exert forces on each other and move around till they reach a relaxed low energy state. And the energy of this relaxed state is predictive of the rate of the reaction, which can be used to determine if a catalyst is good or not. And although I'm showing just one example here, there's billions of adsorbate catalyst combinations that are possible, and simulating each of these accurately with density functional theory calculations takes in the order of 24 hours, which is why there's a need to approximate them with machine learning so that we can bring it down to a few seconds and screen a much larger set of materials to find promising catalysts. To start studying this problem, a couple of years back, we released the Open Catalyst 2020 or OC20 dataset. The dataset consists of 1.3 million DFT relaxations, which can be used for training and evaluation. Our largest training split has 134 million examples, and all of this data is publicly available at opencatalystproject.org. This dataset forms the foundation of the Open Catalyst Challenge. This is what teams used to train their models on.
Similar to last year, the task for this year's competition was IS2RE. That is, given an initial structure, models are tasked with predicting the energy of the relaxed structure. Typical pipelines for IS2RE start off by converting these structures into graphs, where atoms are represented as nodes with edges connecting to neighboring atoms. These graphs are then fed as input to graph neural networks to predict the energy of the relaxed structure. This is what we call the direct approach, and the only form of supervision it needs is IS2RE data, that is, data consisting of initial structures paired with relaxed energies as annotations. An alternative approach is to feed in these initial structures to neural networks to predict the force on each atom. These forces are then used to iteratively update the atomic positions till the max force per atom is close to zero. The structure we obtain at this point is referred to as the ML predicted relaxed structure, which can then be fed into another neural network to predict the energy of that structure. This is what we refer to as the relaxation-based approach, and it typically requires intermediate trajectory data available in the S2EF datasets. So overall, there are two common ways of approaching the IS2RE task. Moving on to some details of the challenge dataset that we asked participants to submit predictions on. This year's test challenge dataset consisted of 100,000 structures. Similar to last year, the test challenge split is further broken down into 4 subsplits: test-like, rotated, anomalous, and dense. These 4 splits are further subdivided into in-distribution and out-of-distribution subsplits relative to the OC20 training dataset. The test-like subsplit follows a similar distribution as OC20 test, and it's used to pick winners. The rotated split consists of a random subset from test-like rotated along X, Y, and Z, and it's useful for evaluating rotational invariance of models. The anomalous split consists of desorptions and dissociations, and the dense split consists of a dense sampling of adsorbate configurations for each add-slab combination, and it's useful for evaluating the recall of lowest energy binding sites. Different from last year, this year we held a single track for the competition, wherein participants were allowed to use the OC20 IS2RE or 2 million S2EF datasets for training. Training on larger splits of OC20 tends to get compute expensive, and so it wasn't allowed for the competition. Note that separate from the challenge, we have evaluation servers open all year round that place no restrictions on the training dataset. And the metric that we evaluate submissions on is energy mean absolute error, calculated as follows. This year, we had 25 submissions overall from 6 teams from around the world. Finally, it's time to announce this year's runner-up and winner. The runner-up this year is Team Atomic Architects from MIT with an energy MAE of 0.427. And the winning team this year is Team TTRC with participants from Tsinghua, the Chinese University of Hong Kong, Tencent AI Lab, and Renmin University of China. Their energy MAE was 0.396. Congratulations to both Atomic Architects MIT and TTRC. This is what the performance of all teams looked like on the test-like split. The vertical axis shows energy MAE, so lower is better. Gray bars are various baselines, and among colored bars, the teams that were within 95% confidence interval of each other are shown in the same color. TTRC achieved 0.396 EV energy MAE, followed by Atomic Architects MIT at 0.427. Relative to spherical channels network, which is our recent approach presented at NeurIPS 2022, that achieved 0.419 energy MAE on the challenge split, TTRC performed 5.5% better. We can also look at progress relative to last year's competition. Last year's winning team, Equiformer by Microsoft Research Asia, achieved an energy MAE of 0.547. Relative to that, Note that most teams this year performed better than last year's winning team, which is great. And TTRC improved over last year's winner by about 28%, which is significant progress. Next, let's look at results on the rotated subsplit. As a reminder, this split consisted of a subset of structures from test-like randomly rotated along X, Y, and Z. All teams achieved similar scores across test-like and rotated, which means that all teams used methods robust to rotations. On the anomalous split that consisted of dissociations and desorptions, models followed a similar ranking, with TTRC and Atomic Architects MIT performing the best. Although overall, the absolute errors on the split were poorer than the test-like split. Moving on to the dense split, like I mentioned earlier, the goal here is to evaluate a model's ability to find the lowest energy binding site. The way we do this is the following. Given several different placements and configurations of the adsorbate on a catalyst surface, we use the model's relaxed energy predictions to select the top K configurations with lowest ML predicted energies and then run full DFT on those K structures. If the lowest DFT energy of these K structures is within epsilon of the lowest DFT energy out of all structures, that's counted as a success. Here, I'm showing what that recall plot looks like as a function of K for an epsilon margin of 0.1 electron volt. Both TTRC and Atomic Architects MIT seem to perform slightly better than our baselines for low values of K, but are largely overlapping after K equals 2. So it seems like models are starting to saturate on this particular metric. Separate from the challenge, in a recent paper that we released on arXiv called AdsorbML, we devised a slightly different way of evaluating the model's ability at finding the lowest energy binding sites. Once again, given several different placements and configurations of the adsorbate on a catalyst surface, we used the model's relaxed energy predictions to select the top K configurations with lowest ML predicted energies. But instead of running full DFT on those K structures, we run single point calculations on the ML relaxed structures. And if the lowest DFT energy out of these K single points is comparable or lower than the lowest DFT energy out of all structures, that's counted as a success. And what we found was that some of our baseline approaches, such as SCN and GEMNet OC, achieve about 85% success on this metric. And since we're only using single point calculations, they can enable more than 1000x reduction in DFT compute. I encourage you all to check out the paper. It wasn't possible to evaluate the competition entries on this metric since we only asked for relaxed energy predictions and not relaxed structure predictions. But we will soon be publicly releasing the dense dataset accompanying the paper to enable the community to benchmark methods on this metric. And it is quite possible that the winning methods of this year's competition outperform our baselines. That brings me to the end of my presentation. Congratulations once again to the winning teams, and thanks to everyone who participated and followed along for this year's competition. The winning teams will be presenting their approaches later in the session, and we should have some members from each team to answer any follow-up questions. We also have a couple of exciting talks by Gábor Csányi and Yoshua Bengio, so I encourage you all to stick around for that. As you all probably know already, all our papers, dataset code, everything's open sourced, so I encourage you all to check that out. We'll share these slides after the presentation, so you'll have access to all of these pointers. And any feedback on the competition in particular or the project overall is highly welcome. There are a number of ways to get in touch with us. You can post on the discussion board or ping us on Twitter or GitHub or email us. And that's it. Thanks, everyone.
Once again, congratulations to all the two winning teams, and honestly, congratulations to everyone. I think it's always exciting to see that plot where almost all results this time around outperformed the winning teams last year. So hopefully we can keep up that progress and get these numbers even lower. So moving right on time, I think we're right on schedule. I believe Gabor is here. Yeah, Gabor is here. Yeah. So let me just go ahead and introduce Gabor. Gabor is a professor at the University of Cambridge. and honestly is well known within the community, and is really a pioneer in machine learning applications to atomic simulations, whether that be molecules or materials. He's really one of those early pioneers. He completed his PhD at MIT, where he did work on density functional theory and electronic structure. But I think he realized that to simulate bigger and more systems, you'd really need to switch to more machine learning applications. So he's really been one of those pioneers and developed some of the early architectures surrounding ML representations for atomic simulations. So without any further ado, Gabor, the floor is yours.
Thank you. Do you see my screen?
Yep.
Okay. So thanks very much. I'm just coming from my group's Christmas party. It's 9 o'clock here back in the UK. So okay, I'm probably not going to fill out the full 30 minutes. There'll be time for some discussion if you like. But I have a few thoughts about how to use ML to simulate to help simulate complex chemistry. And really, I want to place this in the context of first principles modeling. So what the way we use ML in my group is not a statistical learning approach, but more of an accelerator, which fits right in with sort of the OC20 philosophy. I think we believe in quantum mechanics. We believe in describing the world using quantum mechanics, but it's extremely slow and inefficient. And we use ML to create surrogate models, which allow us to then bring this first principles approach to higher length scales, time and length scales, essentially. The factors that of speed up that we're looking for are really in the millions and billions. So first, just a word about ab initio molecular dynamics, the first principles quantum mechanics that we use to study materials. Really, it's a microscope for atomic scale processes. So I just collected a couple of examples here from the recent literature. So if you look at one of the things you can do when you use first principles MD is to investigate phase diagrams. So you take a material like carbon and you ask what is it? What does it look like? What does carbon as a material look like under various temperature pressure conditions, and especially those which you can't access easily in the laboratory, or even if you can access them, you can create them, but then you can't easily study the material under those conditions. So here's a temperature pressure phase diagram going up to 10,000 degrees, and in pressures going up to 2,000 GPa. Right? I mean, the Earth's core is about 400 GPa. So this really is the conditions are extreme here, and we can use density functional theory and the MD based on that, and very big computers, and a lot of skill and craft in using these expensive methods to figure out what the structure of a material is. Something that's much more benchtop is aqueous solutions. So that's going from extreme physics to chemistry now. And people have used density functional theory and molecular dynamics based on density functional theory to study solvated ions. So polyatomic ions, complex ions, not just an atom with an extra or missing electron, but all these ions, polyatomic ions that are here. You can measure their sort of solvation free energy, but really what you can't measure is the structure, the solvation structure around what is the solvent doing around these ions. So if you have if you benchmark the simulation and you get the right solvation free energies, which is what I'm showing you here from this paper, the really excellent match with experiment, then that constitutes the validation, which then allows you to look at the detailed atomistic structure of these liquids. And the third area I picked, where DFT-MD is absolutely ubiquitous and aids our understanding of materials, is surface science. And it's getting, it's one step, the broader context of which certainly heterogeneous catalysis is basically a part of surface science. And in this paper, people were looking at the DiO2 110 surface and an adsorbed molecule on top. And on the left, you see an experimental plot, and on the right, you see the structures, the matching density functional theory computed structures of a molecule as it binds to various sites on this surface. And this allows detailed understanding of such interactions. So in fact, this ab initio MD is so ubiquitous and important that if you take a civilian computing facility, HPC computing facility, and Archer 2 is the national facility in the UK, the largest capability, then these are the programs that people run on it, and I've colored them just green for ab initio MD, DFT basically, and red for molecular dynamics, not with DFT, not with electrons explicitly. And you can see that if you add up all the green bars, you get to about 40% of the total civilian supercomputing time in the UK is spent doing DFT MD. So that is the prize, right? If we could help speed that up using ML, using potentials, then we are making an enormous step change to, depending on how you want to do it, either we eliminate, we free up 40% of the use, or more likely, we enable the same scientists to study, who consume that resource to do much bigger systems for much longer timescales and doing sort of new science. In this little inset, I have the customary range of materials modeling methods, doing quantum chemistry on the way on the left, in terms of timescales reachable, DFT, and then interatomic potentials on the right, and finite elements up here at the top. And I sort of lumped all the electronic structure methods into this green category that we have here. So in this for this community, it's a sort of intersection of computer science, machine learning, and materials modeling. I'd like to stress just how unique a role machine learning can play in this space, in the space of quantum mechanical, as a quantum mechanical surrogate. So from a very, very, very simplified perspective, we can think of the very traditional ML problems like voice recognition, dialogue, or self-driving cars as a way to make something cheaper, something that we already know how to do. We as a society, that image recognition by humans exists and is pretty good. Chatting exists, and driving certainly exists. What is really hard about these things is to do them with a computer. And of course, for very good reason, it's cheaper, scalable, and so on. And achieving these tasks and doing them well does change our lives in the long term, does affect the economy. But for electronic structure, we are actually setting ourselves to solve problems that were actually not solvable before in any way, to the level of accuracy, to the level of usefulness that we demand. So they were basically because they're completely impractical. So density functional theory scales typically as the cube of the system size. There are linear scaling versions with some caveats and extremely high crossover. And beyond the FT methods scale even worse. But certainly what they cannot do is basically take a protein, take a drug-like molecule, and accurately tell you whether that molecule binds to that protein. Of course, the pharma industry has crude models of that, but that's like essentially your image recognition giving you 60% false categorization, right? Of course, these methods exist for molecular interactions. They're just not very good on the scale of a protein. Something closer to my own background is the study of materials, material structure, and amorphous systems. And here, the example task would be to take 100,000 atom system that I have here on the right, of an amorphous system, something like quenched silicon, amorphous carbon, and just know what the structure is. Because if you do that, we know that if you do that with an empirical model, you get it wrong, very basic, it fails very basic checks. And so these are the kinds of tasks that we have just not been able to do up to now. And hopefully ML enables us to do them. So this field of applying ML to atomistic modeling is about 15 years old in the sense in which I'm going to talk about, in the sense of accuracy, speed, and convergibility. And it really started with these two papers. In 2007, Jörg Behler and Michele Parnello applied rather, from looking back from today, a rather simplistic feed-forward network of 2 layers. That wasn't the important thing. The important thing was the recognition that these methods are applicable and using a description, a many-body description of the local environment of an atom. And that was that opened the floodgates. Our paper came a little bit later, very similar, a description of the local environment, and we used Gaussian processes, a kernel method, essentially linear regression using the kernel as a basis, using linear algebra. These two methods have some, actually quite a lot of theoretical commonality, even if the implementations are quite different. And using these techniques over the past 15 years, we have shown that this is the way to do molecular dynamics, at least certainly for materials. One way to say this is that the short-range quantum regression problem, where you have a given set of given material, a given task, a given MD problem, you can solve that with ML. And in 2020, I went around saying that essentially we know how to do this. That doesn't, of course, mean that improving these solutions isn't possible or it's not desirable. It is. And of course, and in the intervening 2 years, significant improvements have been made, mostly by others, actually. So here's an illustration of the kind of benchmark that OC20 is for in 2022, from 10 years earlier. So the QM9, which many of you will know, is 134,000 molecules. QM9, the 9 means 9 heavy atoms, and these people led by Anatol von Ihlenfeld have eventually generated, or rather took this data set. I think the data set itself, originally the geometries are called GDB9, the molecular graphs, and they've created them, relaxed them with DFT, obtained energies and other properties. But what I'm showing you here is the ML prediction of these energies as a function of the number of training points. Now, remember that there's only 134,000 here, so the right-hand side here is where the data ends. And this plot is from 2020. So one thing that is really interesting about this task is that if you have a model that solves this task well, you can claim some glory, but you don't have a model that is actually useful in itself for anything, right? Because the input to these models is the relaxed, DFT relaxed geometry of a molecule. And once you have that, then you know its energy, because that's how you obtain the DFT relaxation. So really, the idea here, and that's really is the idea behind a lot of these very widely used large benchmarks, is that if you do well on this task, then you are capturing something interesting, something important. If you do much better than another method, you are doing something inherently more interesting and suitable for this problem. And therefore, and this is the big if, when you then go on to make a model for a real task that is actually useful, then your model will be better, right? Because here, in order to predict for a new, just once again, in order to predict use the model for a new molecule, you have to have its geometry, and therefore you will have known the energy already. So the other thing to say about this graph is that I've grouped the methods that we could find in the literature in 2020 into using the kind, according to the kind of ML that they use. So we have GPs, kernel regression methods, we have linear regression, and we have neural networks. All of these are message passing neural networks on the right. And what's interesting here is that for this task, the kernel methods really trumps everything else. And these are log scales on both horizontal and vertical. And this, of course, this is not what the picture looked like in 2014 when this data set was released, but the competition was actually extremely useful. And that is what I think the OC20 can, excuse me, can also do, is that over the years, these curves have come down on the vertical axis considerably, just by having been published and people were seeing each other's work, and everything. The things were tuned to really over a decade, an order of magnitude improvement over a number of years on the y-axis. So all of these descriptors and the kernel methods and some of the other groups that have taken part in this effort between essentially 2012 and 2018 have come together for a special issue of Chemical Reviews. And I'd like to highlight two papers that I was involved in, which really summarizes the first 13 years of ML for materials and molecules in the field. So it doesn't include anything from 2021 or 2020, but the first paper is about representations and symmetry and geometry, and was sort of spearheaded by Michele Ceriotti. And the second paper is on the Gaussian process regression modeling and how to assemble data sets, how to train them, how to regularize them, and how to get observables. And that's in the second paper. So I highly recommend this. I'd like to also highlight science applications. These are not mine. These are by people from others in the field, collaborators and friends. And what they illustrate is that these methods are not just promises. So new science is now being done, and this is the way to do material science nowadays. So the first paper I'd like to highlight is from Karsten Reuter's group, and it is actually to do with catalysis, although there aren't any molecules here, but a catalytic surface. So this is an iridium oxide surface, and what was known is that these surfaces can be very complex, and when you look at them under a microscope here, it's an experimental image, then you see structures that are hard to explain, and many times, depending on the conditions, you see unexpected things. So what Karsten's group did is take one of these models. It's highlighting this because I know about it, because this was our software using the SOAP descriptor and the GAP Gaussian process model. They've trained that model on iridium oxide and its surfaces, and then it simulated annealing. So that's a global optimization method, a very large number of relaxations of the surface. And they did that under different oxygen chemical potentials. So essentially under the different oxygen reduced conditions, oxygen deficient conditions, that is actually the realistic condition when this catalyst is in operation. And what they have found was rather stunning from a surface science perspective. So they found entirely new kinds of surface reconstructions, and they call them complexions, because typically a reconstruction is something that happens when you cut a surface and it rearranges. But here you need to actually change the stoichiometry, and they found it is the most beautiful one that matches precisely the experimental data that had hitherto been unexplained. And what this shows is that we don't even know what these materials look like before we put them through before they interact with molecules and before they start to do the catalysis. We have no idea what the surface of materials look like under the conditions, and this is still at 0 K, mind you, and a lot of catalysis happens at elevated temperatures. So so there's still a lot to discover, even on the basic structural point of view, and none of this work can be done without ML potentials, because empirical potentials are not fast enough, and DFT and not accurate enough, and DFT is just far too slow. A second paper that came out recently from is first authored by Bin-Ching Cheng from Michael Cherriotti's group, and it looks at the structure of high-pressure hydrogen. So this is again one of those extreme conditions that you can't simulate in the laboratory, and it's relevant for planetary science. A third one is from the group of Volker Deringer. He's a professor in Oxford, and he was a fellow in my group a few years ago, and they're really taking this idea of complex chemistry and large-scale simulation to a new level. So I have a separate slide on this. These are phase change materials. So this is germanium antimony telluride, which is it's sort of similar to what you have in Blu-ray discs. So it's kind of memory where you pass a kind of a current through with a pulse, that the material amorphizes, and if you pass a different shaped pulse, then it recrystallizes, and this is the memory. So this is the bit. So the two different states of the material have different resistances, and they trained the model, they validated it on a small system that it does the right thing, the same thing as if you did ab initio MD, which you can do on a small system. And then now you can take an actual device, like a 20 by 20 by 40 nanometer cell of this phase change material, and simulate the real pulse on the real time scale, and get and verify that this does the right thing. And then you can go and do the actual science that you want to do, which is pulse shaping. So the ongoing work of this group is to see what kind of different pulses you can put through this material, and what sort of structures you can get. Can you, for example, use this as an analog device by not just having fully on or fully off, or can you have multiple states? Can you store not just one bit, but perhaps 3 bits in a single device, and so on, which is very would essentially be impossible to do carefully and controlled in experiment, because you don't know, you can't in situ, you can't gain insight into the structure. So I'd just like to sort of wrap up with a couple of slides. One, and the two which just illustrate current work, and I've chosen current work that's to do with catalysis on the occasion of this this talk. And the first one is again a collaboration with Carsten Reuter's group, and it's we're looking at rhodium. And I've chosen these examples to show you what you really want to do. So benchmarks are all very good because everybody can do the same thing. And but actually, as I said before, with relation to QM9, what we actually want to do is not find just the binding energy of a molecule on a surface. That's just the start. But actually, we want to investigate mechanisms. So here are a couple of examples where we create ML potentials to investigate mechanisms. The first one is carbon monoxide, eventually going to either methane or methanol. And the first step of this is a CO going to COH. So here's COH on CO plus H, and then when this hydrogen comes and attaches itself to the carbon, then you get this COH molecule. And we have a reaction coordinate here, so there's a distance between the hydrogen and the carbon, and an angle of the CO to the surface, and as theta. And so we've chosen this reaction coordinate that's just a linear combination of this of these two variables, and we perform umbrella sampling. So we drag the system using MD, using the fitted potential along this reaction coordinate, and keep iterating and refining. We always build our data sets iteratively, fold back new configurations. So here you can see the sort of energies and forces of as we iterate along this trajectory. The iteration is several. Each iteration consists of going through the whole reaction and just improving and improving and improving our model. And once we have that, we can actually then turn to the science of catalysis and ask, what is the barrier for this reaction but not at 0K, not at the minimum energy path, but at finite temperature. So the operating temperature in this typical catalyst is 500K. So if you look at the zero temperature profile, then it looks like this. This is with two different DFT functionals, just to show that even that, of course, has a big role here. But this is what you get when you do it at zero temperature, the minimum energy path. But once you do this with MD at 500K and you look at the free energy barrier, then you see something quite dramatic. Certainly with this functional RevPB, essentially this barrier disappears almost to nothing. So this remaining barriers is essentially on the order of a couple of KTs. So it's non-existent. So what we learn here is that this CHO molecule is not really stable. It's not a stable intermediate of this reaction, and that goes counter to the established reaction pathway for this reaction. If you change the functional, then the barrier goes up a bit, so it's 5 KTs and not 2, but it's maybe more like 9. But certainly it goes in the unexpected direction. So people think that people have thought before that at high temperatures these barriers would go up rather than down. A second example, again on catalysis, but a bit more broadly, is on indium oxide. We want to build a potential that can not just look at one reaction, but the whole reaction cycle. So here it's CO2 hydrogenation to methanol, and the training set is bare surfaces, intermediates on the surface placed with CatKit, and a couple of rounds of iterative training on the paths. So what we get when we do that is an ML potential that can do this entire reaction cycle, and so you see the very end here, and it can converge the minimum energy paths that eventually determine the rates. And we're looking at convergence here, but even the 0th iteration, when we just throw in the various fragments onto the surface, is really quite good. The black here is the DFT, the well-known DFT answer, and the various colors here are iteration. And here's what the reaction pathway looks like as it converges to the DFT for this third step. So once we have a potential that's good, we can do things like the following, where we take the CO2 originally and we just look at its binding energy on the surface, but not just one relaxation. There isn't one binding energy. There are many, many, many different states that this molecule can take. And every white blob here is a local minimum of CO2 found with global optimization using the potential and subsequently verified using DFT. And what it shows is that rather than the one state that people have looked at and what we use to benchmark the reaction paths, in fact, there is dozens and dozens and dozens of different inequivalent reaction binding sites here. And here I'm showing you all of them, just colored according to their energy. And the active ones, the ones that take part, so the red is a very high energy, the blue is very low energy, but actually the blue represents the poisoning of the catalyst. The first reaction is, this reaction starts with the physisorb state. So all the sort of grayish white that you see here are potential candidates for this reaction, and largely unexplored. So that's for the future, revealed by this simple ML model. So we are now engaged in understanding how best to build these databases. What do you do when you know not very much about the system? How can you, with minimal effort, build up databases that allow you to study a system? And we are one of our recent ideas, you can find a preprint on the archive server for this, is hyperactive learning, where we take the idea of active learning, where you want to bring in new configurations where the uncertainty is high, where you don't know about it, but better than just bring them in, we want to seek them out. So we take a clue from Bayesian optimization and create an acquisition function here, which has the potential energy minus the constant times the uncertainty. And we do molecular dynamics on such a potential energy surface, which will keep the energy fairly low, but go towards high uncertainty regions. And there's some stopping criterion. We've applied this to perovskites, and I just want to show you this movie where we start this off after 3 iterations, we stop, insert things into the DFT. After 6 iterations, it looks like this. And after 16 iterations, 16 new DFT configurations found by this method that aggressively goes out and looks for things where the model is uncertain, you actually get a stable model of a hybrid perovskite. Where there are some molecules and an inorganic layer interacting. And this system is very interesting for photocatalytic applications, showing 3-phase transitions. And here I'm showing you the experimental transition temperatures compared to the modeled, to the ML model. And we can do this on a large scale with tens of thousands of atoms, which certainly isn't possible before. So I want to close by saying that that really, I think uncertainty quantification is where the current state of the art is, both for building databases, but also for asking really new kinds of modeling questions. So the forward problem is that given some small database, how does the accuracy of the fit that I do, MAEs on energies and forces, how does that determine the accuracy of the material properties? And that's the forward problem. But really, there is an inverse problem, which is given that I want to study a certain material, I want to study a battery, a catalytic system, I want to study hybrid perovskites, what do I need to put into the database? How do I make a mathematical link between the material property that I want and what's needed in the training database to obtain, to give a good prediction? And I think this is really where the future is. I have no idea how to formulate that properly, but this is what keeps us up at night. So thank you very much, and I'm happy to discuss, but I realized that I've just about used up my 30 minutes.
Thank you, Gabor. We are out of time, but we can take 1 or 2 questions if anybody has. Feel free to unmute yourself or send it in the chat.
Nobody else has a question. Gabor, great talk. I have a question, which is, for the ML folks, do you have any advice for the ML community about how you'd like to see the models developed or make them easier to use? But people who are outside of chemistry a little bit, who might just be looking at this from a more of a machine learning perspective.
I think there are multiple ways to get involved and multiple stages. One thing that's very, very different that I of course, I'm sitting on the other side. I'm only looking at the computer science community from the outside. But my impression is that the turnaround, the pace of life is much faster in computer science. And partly because there is an enormous amount of shared understanding of what's important and what you have some benchmarks which and this the past 20 years has shown, you have benchmarks which are very hard, and if you make a big improvement, if you reduce the error by a factor of 2, then everybody should be doing what you're doing. And the computer science community has kind of embraced that in a way that I've never seen in any part of science. People are stuck in their ways everywhere else, but no, in computer science, if you're not doing what everyone else has been doing for the last 2 years, you don't play. But in material science and chemistry, that's a little bit different, actually. Projects are hard, but they're hard on a longer time scale. So even if I can give you a benchmark, please improve this. But even if you do, that's not where the science ends. That's where it starts. And then making an impact in the real world, in industry or even impact in the other modeling community is the next 2 years of using that tool, characterizing it, seeing how it works. So I think it's very, very difficult to make a lasting impact by winning a benchmark test only, right? And I think the computer scientists who are doing in the long term doing well have teamed up with people in the chemistry community and worked together for several years and become conduits of new techniques. That's what I'm saying. And I'm trying to do that from the other side. I'm teaming up with mathematicians, with computer scientists, not for one project, not for one idea, because the idea that we dream up today will make it into codes and be useful in 2 years, and there's a pipeline. So that's, I feel, is the biggest difference, and it's a cultural difference. Yeah, that's my observation.
Thank you. In the interest of time, we should keep going just to catch the other invited speaker. We do have another question in the chat asking about what are the current limitations in ML. I think that's a pretty big question regarding the
I'll type some random thoughts into the chat if you want.
Awesome.
Yeah.
Appreciated. Thank you, Gabor. All right, moving right along. We have our first talk from our runner-ups, Atomic Architects. I see Tess and Elon in the call. They did prepare a pre-recorded video of an overview of their approach to the challenge. So we'll go ahead and play that first, and then we have some time for Q&A at the end. And as always, there is a discussion period at the end. So if we don't have time to get into the questions, we can defer to the end as well. So let me go ahead and share that.
Hello everyone, I'm Elon, and today I'm going to present our method Equiformer+SCN for the Open Catalyst Challenge at NeurIPS 2022. This is the joint work with my advisor, Professor Ted Smith, and we are from MIT. Here's the outline of my presentation. First, I will briefly introduce the Open Catalyst Challenge. Second, I will discuss our method, which consists of the 3 parts: Equiformer, spherical channel network, SCN, and a combination of Equiformer and SCN. Finally, I will present some experimental results. The discovery of efficient catalysts are needed to address the energy challenges posed by climate change. One common approach in discovering new catalysts is running relaxation with molecular simulations. For example, in this figure, we first place a small molecule called adsorbate on top of a large material surface called catalyst to form an initial state. And then we estimate their interactions, such as forces, to update their atomic positions. And then we obtain the relaxed state and relaxed energy. After the relaxation, we can use the relaxed energy to determine important properties, such as reaction rates. However, running a relaxation can take many hours, and there are billions of adsorbate catalyst combinations, which make the previous mentioned approach computationally infeasible. The reason lies in that molecular simulations are performed with compute-intensive density function theory, or DFT. Therefore, the goal of this challenge is that we want to approximate the compute-intensive DFT with AI models or graph neural networks so that we can reduce the time of running a relaxation from hours to seconds. As illustrated in the figure, we take 3D atomic positions and atomic number as input and construct a nearest neighbor graph for a graph neural network to predict the energy and force of this structure or directly predict its corresponding relaxed energy. And there are 3 tests associated with the data set, which are S2EF, structure to energy and force, IS2RS, initial state to relaxed state, IS2RE, initial state to relaxed energy. Our method for this challenge consists of the 3 parts: Equiformer, spherical channel network, SCN, and combining Equiformer and SCN. For Equiformer, it is a graph neural network leveraging the strengths of transformer architectures and equivariant features. Based on typical transformers in natural language processing and computer vision, we introduce 3 modifications. They are equivariant erased features, equivariant operations, and equivariant graph attention. I will briefly discuss them in the following slides, and please refer to our work, Equiformer, Equivariant Graph Attention Transformers for 3D atomistic graphs for further details. Since we are modeling the behaviors of atoms in 3D spaces, it is important to consider 3D-related inductive biases, such as rotational equivariance. For example, as shown in this figure, when we rotate the molecule, we want some properties, such as forces acting on each atom, to be rotated accordingly. To incorporate such inductive biases, we use vector spaces of irreducible representations, or IREPs, as internal feature representations. More concretely, the IREPs features contain vectors of different types, and two common examples of such vectors are scalars, or type 0 vectors, and Euclidean vectors, or type 1 vectors. Since the internal representations are now equivariant IREPs features instead of typical scalar features, we need equivariant operations to transform those features. The operations consist of two parts. First, we replace original operations in transformers with their equivariant version. They include linear layer normalization, and activation function. Second, we introduce additional tensor product operations to transformers in order to mix the information contained in vectors of different types. For example, we can use tensor products to mix the information of scalars and Euclidean vectors. Finally, we improve the expressivity of typical dot product attention with equivariant graph attention. This is based on the observation that in attention, the feature MTS sent from source node to target node can be formulated as the product of attention weights and value vectors. Therefore, for better expressivity, we can use nonlinear functions consisting of tensor products to generate both attention weights and value vectors. With the three modifications, we can convert typical transformers in natural language processing and computer vision into Equiformer, a powerful transformer for 3D atomistic graphs. The overall architecture of Equiformer is shown here. After processing the input 3D graph with many Equiformer blocks, we perform global sum aggregation to predict energy or relax energy, and use IREPs features at each node to predict forces acting on each atom. In addition to Equiformer, we also consider spherical channel networks, SCN, proposed by Meta AI. Instead of using equivariant operations, SCN uses non-strictly equivariant operations, and it has demonstrated impressive results on the Open Catalyst 2020 dataset. Roughly speaking, SCN uses standard operations to trade equivariance for better expressivity and efficiency during both message passing and message aggregation. I will briefly discuss them in the following slides, and please refer to the work Spherical Channels for Modeling Atomic Interactions by Meta AI for further details. For the message sent from source node to target node, SCN first rotate node features with a rotation matrix for which the relative position will be aligned with global z-axis. And then it extracts a subset of M components in these IREPs features and treats them as pure scalars. Instead of using equivariant operations, SCN applies standard layers. Although this breaks equivariance, they find relaxing the constraint of equivariance can improve the performance on OC20 datasets. As for message aggregation, SCN converts IREPs features into point samples on a grid, operates on 2D sample grids with standard layers, and converts back to IREPs features. The conversion to samples on a grid uses discrete sampling and is therefore approximately equivariant. We consider the combination of Equiformer and SCN as our final method. The motivation is that recent computer vision models combine convolution with inductive biases and transformer blocks with less or no inductive biases in order to achieve better performance. So this inspires us to combine equivariant attention of transformer blocks with non-strictly equivariant attention built from SCN operations and present our method Equiformer plus SCN. Here's the overall architecture of Equiformer plus SCN. We can use the message passing and message aggregation proposed by SCN to build the corresponding transformer blocks as shown here. We process input 3D graphs with Equiformer blocks on the left branch, and then with SCN blocks on the right branch. We sum the equivariant output and non-strictly equivariant output as the final output of our network. The training details are shown here. For our network, we use 6 Equiformer blocks with degree up to 1. We have 12 SCN blocks with 4 taps, 2 bands, and degree up to 6. We use a smaller version of SCN with smaller hidden sizes and less hidden layers. We construct nearest neighbor graph with a cutoff radius of 5 angstrom. We train networks with cosine learning rate with linear warm-up. We consider 2 approaches, relaxation and direct, to predict relaxed energy. For relaxation, we train on S2EF TM subset. For direct, we train on IS2RE dataset with IS2RS auxiliary task and noisy nodes data augmentation. The training time is 1,632 GPU hours for S2EF and 632 GPU hours for IS2RE when A100 GPUs are used. We compare the results on the validation set between models with the direct approach. As shown in this table, Equiformer plus SCN achieves the lowest mean absolute errors when only IS2RE and IS2RS data are used. We also report the results of Equiformer plus SCN on the test challenge split. The relaxation approach achieves lower error compared to the direct approach, while training on S2EF requires about 2.6 times more computation. And this is the end of my presentation. Thank you very much for your attention. Please feel free to reach out to me if you have any questions.
Thank you, and congratulations once again. We have time for a question or two. We are playing catch up on time, but we do have time at the end, if anything. I guess while people gather their thoughts, I had a question. What I found interesting was when you showed the combination of Equiformer and SCN, that you had Equiformer go up to L equals 1. And I think this is something I've seen in the literature, like NeurIPS and other equivariant models don't really leverage higher Ls, but you do leverage SCN to higher Ls. Is there something about relaxing equivariance that takes it more advantage of the higher Ls, or is there a specific reason why Equiformer didn't leverage higher Ls?
Can you hear me? Yeah. I guess the reason is just because when I use L up to 2, I do not observe too much gain at my initial experiment, so I didn't use L up to 2. But it seems that if we use more channels and spend more time, the performance can improve if we use higher L, like L up to 2 or L up to 3. Yeah. And I guess for SCN, because it uses standard linear layers, so it is much easier to scale up to L up to 6. But I think it might be interesting to use like higher L for Equiformer. But I guess the problem lies in either computation and also how these operations can be optimized. Yeah. Yeah, is that answer your question?
Yep, thank you. We have one question in the chat. When does the non-equivariance help? Or like when does relaxing equivariance help?
I think if we use non-equivariant operations, we can just use standard operations like typical linear layers in other in networks in other domains like computer vision and natural language processing, and those operations are well optimized, and so we can use so it is much easier to scale up to higher L, like L up to 6 in XCN, but it is very hard to use L up to 6 in Equiformer. But I guess there will be some trade-offs. So for the open catalyst dataset, maybe we can use these approximate operations to scale up to higher L, but it is not necessarily mean that we can use this approach for other datasets or like smaller datasets like MD17 or QM9.
Thank you. Any other questions? I guess, Elon, this is a quick one. You have a combination of SCN Equiformer. Do the force predictions you make, are they in a similar manner to SCN where you directly predict forces, or do you guys do predict energies and take a gradient with respect to positions?
I use a direct approach. So yeah, I guess I observe slightly faster convergence compared to just SCN. But I trained a much smaller version of Equiformer, but a much smaller version of SCN. So it's very hard to say whether the performance gain can lie in attention or layer normalization or equivariance part. But it might be interesting to answer those questions, but it takes much computation.
Yep, sounds good. Thank you. We'll move on, and if you guys are still around at the end, I'm sure people can ask more questions there. All right. So those were our runner-ups, Atomic Architects from MIT, Tess and Yelan. Next, we have our winners for this year's competition, and that is TTRC. They have a large team, and I'll let them introduce themselves in their talk and let them share about their approach to GeoEnsemble. I think I see a few of them here, so they can take questions at the end. There we go. Let me go ahead and share that. And I know you guys are at the other end of the world, so it's probably really dark there.
Yeah, it's just about the morning.
Oh.
Okay.
Okay.
6 o'clock.
Yeah. Okay, let me go ahead and play this.
Hello everyone, I'm Jiaqi Han. Here I will introduce our approach named GeoEnsemble for the Open Catalyst Challenge 2022. Our team members include Jiaqi Han, Tian Bian, Ge Yanye, Kaili Ma, Yu Duozhi, Kangfei Zhao, Tingyang Xu, Wenbing Huang, and Yu Rong. The members are with Tencent AI Lab, Tsinghua University, Renmin University of China, and the Chinese University of Hong Kong. The Open Catalyst project aims at tackling the energy scarcity and climate change issue. For instance, in China, a majority of electricity production is fueled by burning coals or fossil fuels. These processes negatively affect the climate, whereas wind or solar energy are much cleaner. The core interest here of the Open Catalyst project is to help discover new catalysts that can efficiently produce clean and renewable energy, thus help reducing carbon emission and alleviating climate change. Specifically, Open Catalyst project investigates the relaxation process of the adsorbate and catalyst from the initial high energy state towards the low energy state, driven by the interactions in between. The energy of the relaxed state is useful in determining critical chemical properties like the reaction rate of the system. In this year's challenge, IS2RE and S2EF2 million data are approved to use in model training and validation. With the task specified, two core challenges are identified. The first is how to model the complex dynamics mechanisms of the interacting particles in both the adsorbate and catalyst, and secondly, how to effectively incorporate the S2EF and S2RE data. Here we present GMNOC, which is our adaptation of graph mechanics networks GMN
Now
on
to
the
start the
OpenCatalyst
last.
data. In GMN, iClear 22, we propose a universal multi-channel O3 equivalent function. Consider the geometric information Z and non-geometric information H. Our proposed form is specified as phi ZH equals Z times sigma, the inner product of Z transpose and Z, concatenated by H. Here sigma is an MLP. This formulation can universally approximate any O3 equivalent function with arbitrarily small error. The corresponding invariant counterpart is also provided as a function per psi. With these specifications, we now introduce a GML layer. We first compute the edge message between node I and j. For example, Zij equals Zi minus Zj concatenated by Rij, where Rij is the edge direction vector. Similarly, Hij is a concatenation of Hi, Hj, and the length of Rij featurized by the Gaussian kernel. The equivalent edge message Mij is computed by calling our equivalent function phi. The messages are then aggregated within the neighborhood determined by a cutoff to obtain the updated node representation. The GML layer satisfies E3 equivariance overall, which is important for model generalization. Now we discuss how to leverage the proposed GML layers to build up a powerful model with enhanced capacity for challenging tasks like OC here. We start by stacking multiple GML layers to build up a deep model with more trainable parameters. We initialize Z as 0 vectors and H as an learnable embedding of the atomic numbers. Both Z and H are passed through several GML layers for effective geometric message passing. And finally, we use the output Z to produce the node-wise geometric vector F, which is the atom force, and the energy for its system, E, as the pooling of the node features H. Furthermore, inspired by the virtual node technique in traditional GNNs, as well as the motivations from density functional theory calculations, which involves computing the global electron density, we introduce a global representation module, which is shared across all GML layers. The global module is also implemented using our GML function phi. To combine the global representation with local representation of each layer, we extra introduce the combination operation, which first uses our invariant form per psi to compute the invariant Wij, and then multiplies the aggregation of W by the global representation V. The computational flowchart is illustrated in the right figure, where we can see that all modules are densely connected to ensure training stability. The force and energy are similarly obtained from the last GML layer. Thirdly, we also equip GML with a multi-head mechanism to further enhance model capacity. In detail, as we can see in the plain GML layer, the bottleneck of parameter complexity lies in the dense inner product matrix, which is of complexity OH², where H is the number of vector channels of Z. This square complexity limits our choices for a larger number of H. For example, if we choose H as 64, we will need a representation space with dimension 4096, which is too large. However, setting H as a small number will inevitably limit the model expressivity. To overcome this challenge, we designed a multi-head mechanism for geometric message passing of GML layers. In detail, for Z, we separate Z into several subspaces split across vector channels. Afterwards, the inner product is only computed within each subspace instead of the global dense matrix. In this way, we are able to reduce the parameter complexity by a factor of n head without shrinking the number of vector channels H. Instead of a dense inner product matrix, now we have the blockwise diagonal inner product matrices within each subspace. With this technique, we are able to significantly increase the number of vector channels when fitting the model into the GPU memory. All the three core aspects we mentioned here are important for the performance of our model on OC data. The overall model named GeoEnsemble is an ensemble of 4 geometric models, namely GMN-OC, SCN by Lawrence Zinting et al., and GEMNet by Gasteyer et al. Notably, SCN AS2RE here is an SCN firstly pre-trained on S2EF 2 million data, and then fine-tuned on S2RE data, equipped by the delta position loss. The relaxed energy is then directly predicted without relaxation. The other three models are trained on S2EF 2 million data, and then applied by the relaxation process to get the relaxed energy prediction. The results of 4 models are ensembled simply by a linear weighted average scheme, with the coefficients determined by validation. The number of parameters of each model are presented in the table as well. Here we provide more details on these models we use. It typically takes thousands of GPU hours to fully train the models. Regarding the inference speed, the direct model is significantly faster than the relaxation models, since relaxation process needs to iteratively call the model forward function until a steady state is reached or the number of steps reaches a preset maximum tolerance. We also evaluate our approach on the public leaderboard maintained by the OC team. The leaderboard here is for the OC21 challenge test set. Our GMN OC model reaches an energy MAE of around 0.42 when trained on S2EF 2 million data instead of S2EF all. Note that some of the methods here on the leaderboard use S2EF all for training, which is larger than S2EF 2 million we use in this challenge, thus the results may not be exactly comparable. Our final GeoEnsemble model with S2EF 2 million achieves an energy MAE around 0.34, which is only worse than the SCN trained with S2EF all data. As future works, we would like to further borrow more inspirations from real physical processes to motivate the design of our model, and meanwhile explore more effective ways of leveraging the existing data. We also believe there are still room for training process optimization on such a challenging dataset of the Open Catalyst. Finally, I would like to thank all collaborators that provide necessary support, significant efforts, and useful suggestions throughout the competition. This is a joint team with members coming from Tencent AI Lab, Tsinghua University, CUHK, and Renmin University of China. If you are interested in any topic or technique we discuss in this talk, welcome to reach out. Thank you.
All right, that was our winning team for this year's competition, TTRC. Congratulations once again. We have some time for questions, so unmute, type it in the chat. We have some time.
It's really interesting how you ensembled everything together. Can you say anything about the relative weights of the 4 different things that went into your final prediction? Were any of them particularly more or less important than the others?
Okay, thank you for reading the question. Can you hear me? Okay, great. We actually just simply adopted a linear weighting scheme for the GeoEnsemble model, where we initially equally weighted each model and dynamically adjusting the ensembling weight by the validation data. And empirically, we found that the weight for SC model is around 0.3 or 0.4, which is actually a little larger than the other models, where the other 3 models actually share the weightings equally. So I think the importance of SCN is relatively larger than other models, but both for models have significant contribution to the overall performance of the ensembled model.
Francesco, sorry if I mispronounced that. Go ahead.
Yes, thank you. Thank you for the hard work. I suppose training all this model was not so straightforward. I have a question. What do you think is the limitation of your model? So why do you think you had to use the ensemble? I mean, we all know the ensemble typically have the help, but where do you think your method needed help?
Yeah. Actually, we share a relatively similar motivation as the last speaker of the run-up talk. We believe that the geometric GNNs in the geometric deep learning domain actually possess unique features varying across different models. Like SCN is approximately equivariant by their unique operations, and our model is actually a strictly E3 equivariant model. So I think that each model has their unique features, and they can all serve as weak learners. So by ensembling all of these models together, we are actually it's more likely for us to obtain a strong learner in this case.
And do you think this not equivariant network, they capture some, how to say, spurious feature? Because in theory, geometrically, they shouldn't be there. It's because they're learning.
I think the non-strictly equivariant models like SCN actually adds to the model more flexibility. It's like the strictly equivariant functions are, like the E3 equivariant functions, they are strictly equivariant on the E3 group. Actually enforcing them with more constraints, it's like their expressivity is constrained by such equivariance constraint. So by relaxing the constraint into a subgroup, or relaxing the model to non-equivariant version, we can add more flexibility to the model. It's actually an operation of increasing the expressivity of the model. So I think in some cases, it might be important to relax the model from full equivariant version to its how to say that? No, strictly equivariant version.
Thank you.
Brendan, go ahead.
Yeah, I was just curious, you guys had a global representation in your model. I was curious, did you do any ablations where you, I'm sure maybe you did, where you didn't include that? Can you talk about how much that helped the performance?
Yeah. Adding the model, I think I remember should have boost the performance by at least 0.03 or 0.04 to the overall performance. So I should say the technique is also very important here. It's like an additional module that we add up on top of the GML layers we have discussed in our iClear paper. And we empirically found that this technique is also very important for the performance.
Great, thank you.
We got time for one more question. If no questions, I can ask mine. I noticed that when you were the model blocks, when you were making the energy and force predictions, you had a Z representation that was initialized from atomic numbers, and then you had one that was a function of atomic numbers and one that was initialized for zeros.
Yeah.
And they fed through your model. What was interesting to me was it seemed that they were independent, so they updated independently and their representations weren't exchanged with each other. Did I understand that correctly, or is that?
In our talk, we refer these notations to Z and H. It's like the vector or scalar. Actually, we can also treat it as type 0 or type 1 vectors. And in our model design, in the video, we actually have discussed how to it's like how to mix up these representations in the message computation. It's like the message computation takes as input the inner product of Z. It's like Z transpose dot Z, and concatenated by the scalar feature H. So it's like during the message computation, these two parts are also entangled with each other. So actually they are not separated, updated in the model. So it's like they are still combined together.
Yep. Okay. Yep. Makes sense. Thank you. All right. Congratulations once again. We have time at the end if people do think of more questions. But moving on to our last and certainly not least talk. I believe Yoshua is in here. Let me just, yep, he's in the chat. So it's a great pleasure to welcome Yoshua Bengio here today. Yoshua is recognized worldwide for his pioneering work in AI and deep learning, earning him the Turing Award in 2018 alongside Yanli Kun and Jeffrey Hinton. He is a professor at the University of Montreal and the founder and scientific director of MILA, the Quebec AI Institute. He's done a lot of work that's too much to cover and too much to overview right here. But more recently, Yoshua has taken some interest in AI for social good, whether that means healthcare, environmental impacts, or more specifically, climate change. So without any further ado, Yoshua, it's great to have you here, and we're excited to hear what you have to say.
Thank you, Mohammed. Thanks for the kind words. Let me share my screen. Okay, hopefully you guys see this.
Yep.
Right, so I'm going to tell you about methods that we are exploring in my group for scientific discovery broadly. I'll say a little bit about the recent work we did for OC20. And in terms of machine learning, I'll talk about these new methods, which we call generative flow networks, or GFlowNets for short. So the general problem that we are hoping to help with is the sort of iterative discovery process. So it's not just the modeling the data, making predictions of energy and things like this, but generally proposing new experiments, maybe new materials in the case of OC20, and doing it, multiple times in a number of rounds, which look like active learning, but is also related to Bayesian optimization and classical work in experimental design and Bayesian optimal experimental design. So where does machine learning come here? There are two main parts, really. One is about the modeling. You've got some data, and you'd like to actually build a Bayesian and causal model that is able to capture all of the theories that are compatible with the data, all of the models of the predictors that are compatible with the data. And then what you want to do is to generate candidate experiments. Usually it's going to be a batch of experiments. These days we can do parallel experiments. And I'll motivate why, instead of thinking of this as an optimization problem, we may want to think of it as a sampling problem in order to get a large diversity of candidates. So yeah, basically the modeling part, which implicitly generates samples of explanatory hypotheses, experimental design to disambiguate them. And then, people are also using machine learning in the experimentation part for using robotics and stuff, but I'm not talking about that. So the thing that I've been thinking a lot about is the search problem of new molecules, whether it's for drugs or for materials, and in particular with applications in climate change, as you said. It's really searching a needle in a haystack, where the space of candidates, or the space of interpretations of the data, if you're thinking in a Bayesian way, is huge. It's exponentially large. And I'll argue in both for the modeling and the experimental design, would like to get not just one good candidate, but all of the good ones if we could. So I'll also argue that we can use machine learning to help us capture that high diversity, that we can represent that as a distribution over theories or over experiments, and that like large neural nets can represent very rich distributions that can play that role. One aspect I also will emphasize is because we're thinking of this not as searching in a fixed list of candidates, like somebody, chemists have built these large lists of potentially useful molecules, but really open up to all the molecules of a particular kind, all the materials of a particular kind, which is usually going to be experimentally large. And so even if we have a good model that can allow us to score how good we think a candidate would be, we won't be able to in the computer even screen like 10 to the 50 candidates or something. So instead, the approach that we're taking, and GFlow-nets are a part of doing that, is to train a kind of generative model, or actually a generative policy, that will sample candidates with probability proportional to their information gain. And actually, the same trick can be used to sample theories, or if you want, like causal graphs and things like this that explain the data. So GFlow-nets are a tool to do just that, to train a policy that samples objects with probability proportional to some quantity that you define. And so if we look at the big picture, it looks, so now putting the machine learning pieces in this iterations, it looks a little bit like model-based reinforcement learning, right? So you've got the real world, you do some experiments, you collect some data. Using that data, you build a model, but you'd like that model to be, I'll argue, to be both causal and Bayesian. And then using that model, which you can query because it's in the computer now, and for cheap compared to doing actual experiments, you train this policy that's going to produce candidate experiments. And so you have this loop where you train the policy, but it's all happening in the computer, right, in silico, so that you now generate candidates that are most useful in some sense. So that's the general picture. Now, why do we want to do something like sampling rather than optimization, like in Bayesian optimization? Because we would like to have a diverse set of candidates. Why do we want to have a diverse set of candidates? Because the way that we are going to evaluate those candidates, at least initially, is going to be a proxy for the real thing. So maybe we have some cheap experiment where, experimental setup where we can measure some properties we care about, but maybe they're noisy, or maybe they are simply biased, or maybe they don't measure everything we care about, but the other things we'd like to measure are just too difficult and too costly. So we'll do that only with a few candidates. And so we have usually we have like in drug discovery, for example, you have a front line of in vitro experiments. And so why does that matter? Because if you generate a bunch of candidates and they're all like small variations on each other, but they're optimized for something that is not quite what you want, they might all not work at the end of the day. Whereas if you try to generate a diverse set of candidates that covers all of the configurations that may be interesting, well, first of all, scientifically, that's more you might learn more things, but also there's less chances that all of those diverse candidates will fail together. So that's the reason for diversity, mostly. So we wrote a paper about this idea of diverse candidate generation using, it was the first paper on GFlow-nets at the last NeurIPS in 21. And again, like the basic outcome of training a GFlow-net is that you get this policy that will sample objects X with probability proportional to a given reward function. So when you train the GFlow-net, you're supposed to give it a function, which is like a reward function like in RL, rather than a data set. So usually, generative models are trained from a data set of good examples. And here, what we have instead is a different setting where somebody can tell us, given a candidate, how good is that supposed to be in terms of what we want, for example, information gain. and then we're going to sample candidates with probability proportional to that. So it's related to generative models, it's related to RL, but it's different. And it actually does something else. It generates those candidates in a sequential way. For example, constructing a graph. So it can be a generative model for a graph, but doing it sequentially allows to represent very rich distributions over these objects, multimodal distributions, something that may be difficult to do with other more traditional approaches. The other thing that comes out of this method is that they give you marginalized quantities, so you can estimate probabilities over like subsets of variables. So marginalization, partition functions, intractable sums can be estimated. For example, mutual information, which is something that comes up in information gain. Okay, so let me dig a little bit deeper into why we need Bayesian posteriors. So if you know a little bit about active learning or experimental design, you want to choose your experiment that will tell you as much as possible about some quantity of interest. And you don't care about doing an experiment that has a lot of uncertainty just because of noise, but only epistemic uncertainty. In other words, the part of the unpredictability that is due to the lack of knowledge, and thus that can be reduced through more experiments. And if you know, one way to do that would be to estimate Bayesian posteriors over like the things you care about, maybe the success that you expect with different materials, or maybe a causal graph that you care to get more accurately. So the mutual information between this quantity of interest and the outcome of an experiment. So one way to think about it is the epistemic uncertainty tells us about how to disentangle multiple theories that we care about and that are compatible with the data. So we apply GFlow nets to these settings where we estimate epistemic uncertainty. This was a paper at ICML last summer called Biological Sequence Design with GFlow nets, including some experiments on DNA-based materials, but also more like health-related questions, for example, searching the space of peptides for antimicrobials and things like that. So the difference with the other paper is that the thing we are training the GFlowNet with is something similar to what we do in Bayesian optimization, these acquisition functions that include a notion of epistemic uncertainty. And we, in this paper, we measure a number of things of interest here. At each round, we want to measure, of course, how good are the candidates according to the experimental outcomes, the oracle that we use to evaluate the system. But as I mentioned, diversity, like how far are they from each other, for example, in some measure of distance. And finally, novelty, because at any moment we already know some materials or some drugs or something for which we know the answer and would like the new candidate experiments to be far from those we already know. So yeah, we did a lot of experiments on different tasks that all in this paper all involve experiment specification in the form of a sequence of, for example, amino acids or DNA letters. And the bottom line of all these experiments is that the GFlowNet variant tends to be either the same or generally better than existing methods in terms of the average performance of the candidates that it generates, but a lot better in terms of diversity, how much the different candidates differ from each other, and novelty, which is sort of side effect of the same property. Okay, so let me dig a little bit more into the Bayesian question. When you're doing science or discovery, you have this problem that there may be, for example, multiple neural nets that are doing a good job at predicting your training data. And if you're interested in causality, there may be multiple causal graphs that are compatible with your data. And if you just do something traditional in machine learning, like maximum likelihood or regularized maximum likelihood, you're going to pick one of them. Think of it like, pick one theory that is compatible with the data. But the problem with that, even though that theory may, fit the data very well and better maybe than even some other alternatives, but slightly better than other alternatives, it could be wrong. It could be that another theory is the right one because you have finite amount of data, and even with infinite data, there's identifiability question, which mean that even in that case, there may be ambiguity about different theories that are compatible with the data. So why does this matter? Because your chosen theory, your chosen parameters could be confidently wrong, right? That the two theories could disagree very strongly on what the answer to a particular question could be. And of course, only one of them is correct, and they both fit the data as well. And that's the situation that really we want to avoid, that we kind of pick one of those theories and then it leads us to a completely wrong direction. Whereas if you were able to handle all of those theories together, so that's the Bayesian posterior, then in case where the theories disagree, you would have a calibrated probability that tells you, well, we don't know what the answer is here. And actually, that's probably a sign that you do want to do an experiment. Now, the actual quantity you care about, as I said, is a mutual information that's going to bring you as many bits as possible to find which theory is better. Okay, now with all this, you might ask, why is it that people have not been people have been working on Bayesian machine learning for decades, but they haven't really made it to state-of-the-art models you hear about in the news. So what's the problem? Well, past approaches. So first of all, if you look at it on the face of it, it's intractable to compute these Bayesian quantities. But so what people have done is use approximations of various kinds, and typically either using Monte Carlo Markov chain methods or using variational methods that make strong assumptions, either about the form of the distribution or about the posterior distribution, so that the calculations, the Bayesian calculations, become easy. And of course, these assumptions are likely to be wrong. In the case of MCMC, you don't make any assumptions, but the calculations can take forever. In fact, it could take exponential time if you have many modes of the distribution you're trying to represent. So that can be a problem. And in practice, it is in these molecular spaces. Now, the good news is that we can leverage the progress that has happened in deep learning. For example, these large language models, large vision models that can represent very rich distributions, to learn to represent approximately these Bayesian posteriors. And so the first paper we wrote on this was presented last August at UAI, led by my PhD student, Tristan Deleu. So these are all the authors, called Bayesian Structured Learning with Generative Flow Networks. And we focus on a kind of simple case here, which is just the Bayesian posterior over graphs, which is already very difficult because the number of possible causal graphs is exponentially large. So given some data of observations of random variables, how do we learn a distribution over graphs that are compatible with the data? That's essentially what this does, and can do it efficiently. Yeah, you can look at that for more detail. Now, we've started working and starting to apply some of these ideas in on the OC20 data set. And the part we've done now, and that was presented at the workshop on AI for accelerated material design, is just the model part, just like focusing, like many others being presenting today, on the prediction of the relaxed energy of the absorbent and catalyst system. So this work has been led by Alexandre Duval and several other people at Mila, including David Rolnick. And it innovates in 3 ways. So compared to the existing pipelines based on graph neural nets. So first, and I'll mention that in more detail, we do something particular about the graph that takes advantage of some of the things we know from a chemical point of view about the task. Then the way that we represent the input, so the atoms, is a bit richer than usual. So instead of just having an ID, a symbol for the atom, we introduce a bunch of features like the group, the period, so the position in the periodic table, whether this atom is part of the adsorbate, the catalyst surface, or the subsurface, and also the atom's radius and density, and potentially we could add other features. And also we've been playing with the architecture of the graph neural net in terms of pooling the outputs near the end in order to come up with the energy prediction with several kind of improvements. So one is that instead of aggregating the information coming from all the nodes in the graph with a simple sum, we do an adaptive weighted sum where we use the graph itself to decide on how much weight to give to each of the nodes. And then we do that weighted sum, but also instead of having a simple sum and MLP, we do this in several steps with a hierarchical pooling, grouping atoms that are close together into sort of super nodes. For the part about how we play with the graph structure, this turned out to be quite important for efficiency. So one of the things we were looking for is not just mean absolute error, but also how fast is this running? And if you look at atoms, as I said, that are in these 3 categories, the catalyst subsurface, catalyst surface, and adsorbate in 3 colors here, turns out that the atoms in the catalyst subsurface are not that important, or the details of them is not that important. And so we could pool all of the information into a single supernode with a special representation. And that reduces considerably the number of nodes in the graph and can really speed things up. Right. And so in terms of results, we compared to SCHNET, D++, and ForceNet using the splits, both in distribution and out of distribution that exists. And we find an improvement both in terms of mean absolute error with those baselines and in terms of speed, like from 3x to 5x improvements. And we find that in general, these improvements are even larger on the OOD splits. Just to finish, we have some current work going related to this, working with the lab of Curtis Billingett, chemist at UBC, sorry, British Columbia, who's working on an electrolyzer for carbon capture. And so you can choose materials here, but you also have something interesting, which is you have access to a kind of visual spectral, let's say, analysis of what is going on inside the electrolyzer, inside the in between the cathode and the anode. You're able to kind of see the presence of gas bubbles that are forming, and we are hoping to use machine learning to control that process in order to make it more efficient. So if you want to learn more about GFlow nets, I wrote a tutorial, which you should be able to find fairly easily online. And there's already like 10 or more papers that you can find in the tutorial on GFlow net. So it started at the last NeurIPS, about a year now. And lots of things have been written for different kinds of applications in probabilistic modeling, but many applications related to the scientific discovery tasks. So I'll stop here and be happy to answer questions. Thank you.
Thank you, Yoshua, for the great talk. Like you mentioned, we have time for questions. Feel free to unmute, send them in the chat. I can start us off while people gather their thoughts. Yoshua, I'm curious, you shared a wide range of applications, specifically various scientific applications. In your experience, what has been some of the biggest challenges in like leveraging deep learning or just machine learning in general to these various problems?
Well, I'm not going to teach you anything here. Depending on the setup, the tasks, it's data, right? And you know, in the OC20, we were kind of all lucky that the resources were put to bear to generate all that information. But that's not even like the real thing. It's experimental data is going to be the real bottleneck, because we are using approximate, molecular dynamics calculations. So I think these, by the way, the example here that I said about diversity applies because we're using an approximation of the real thing, which are the real experiments with synthesized materials. And it's not the real thing. So we're optimizing with respect to the wrong thing. And when we're doing that, we want to make sure we don't put all our eggs in the same basket. That's why the diversity is so interesting as a concept to bring in our fold. But yeah, data, the ability, so once you start thinking from this active learning perspective, where there will be multiple rounds of iterations, and the oracle could be calling some molecular dynamics thing or an approximation of it, and you can have a trade-off between the cost of that and its fidelity. But once you start having these loops, it raises all kinds of questions that go well beyond what we just think about if we're just trying to, get mean absolute error low, right? This is really interesting from a machine learning perspective. And also from the experimental side or the oracle side, computation time becomes a bottleneck. Like if it takes a week to get an answer, it's not the same thing as if it takes 1 second, because you can do a lot more experiments. But you want to use active learning in order to be efficient in deciding where is it worth putting your compute or your real experiments.
Yep, absolutely. Thank you for that. Larry, go ahead.
Thanks for the good talk, Yoshua. Just a note on the experimental work is one thing that we do hope to do sometime in the not too long future is to release some experimental results as well. Because one of the issues that that we've seen is, a lot of experimental papers that are out there tell you the good, the good materials. So you know what I mean?
Yes.
From an ML perspective, we want not just the good results, we want the bad results as well.
Yes.
To start kind of, looking at these models and seeing if the computational results that we're, generating link up to the experimental work. So I think it'd be really valuable to the community to create that. And, but it's a lot of work. It's much harder than generating computational work, but hopefully we'll have an update on that, in the not too long future.
That would be great.
The other thing is, you brought up a really good point, and this is something that we've been thinking of as a team a lot, which is, how do we come up with, confidence metrics for the models? Because we're really worried that these ML, potentials that we're developing, et cetera, they won't be as useful to the chemistry community, to the material science community, unless we can provide to them some sort of metrics for how confident we are in the models. And, all the first stabs that we've taken at it, none of them, are really that good, or that indicative of, they're not as. So
what kind of things have you tried?
Yeah, just looking at ensembles, things like that. Kind of like the first things that you would try. None of them, offer really great.
Well, you could see why an ensemble is limited, because if you have an ensemble of 5 networks, then at most you can represent 5 modes of the distribution, the posterior distribution.
And it's even worse if it's the same model, like the same architecture.
It's even worse if it's the same model. That's right.
So one thing that when you were talking, one thing I was thinking about is how can we encourage the community to look into confidence intervals a little bit more? Because it's something that we're not tracking on the leaderboard. You know, it's not.
Yeah,
I feel like a first-class citizen. You know what I mean? But I feel like it
you're
should.
right. Yeah, it's a good question. Well, you could just measure the marginal log likelihood. So in other words, people have to not just output an energy, but also a distribution over that. And that would already, and that's something you can score using just log likelihood, out of sample log likelihood, right? I mean, it's just the same thing. But now, if somebody say doesn't use any calibration, like use a single model, they can have catastrophic log likelihood. Like if you're very confident that the energy is at some value and you're off badly because of your confidence interval is too small, then you're going to pay a big price in log likelihood. So it's a fairly agnostic way of estimating how accurate these confidences are. I mean,
do you know of any good benchmarks that are doing that now?
I don't know. So what you want to measure, okay, so let me maybe more just to make sure I'm clear. The person doesn't output a number which is say a prediction or a number that would be a probability. They output a function that you can call, and you're going to call it with the right answer. It's going to be, they provide P of y. Y is the quantity you're trying to predict, or log P of y, and then you call it and you measure it on the ground truth that you hold secret. And of course, they can do it on a validation set, right? So it's just log likelihood, right? Test log likelihood. Now, they might do it with a Gaussian if they want, and then they have a mean prediction, and they're going to have some variance. It's their game. You shouldn't force them to go into the Gaussian game.
Makes sense. Yeah, maybe we can follow up later, but thinking about how we can make this a metric that people can follow, especially if it's not something that's well studied in other domains. Like this one's just such a critical to have this work, because DFT, if you give DFT garbage, it won't converge, but these ML models, they're overly confident like all other ML models. So
right. So the other thing is you can use that even within the sort of physics or chemistry based calculations, so long as they can give you probabilities, because so in this way you can check how likely are the predictions made by a cheaper approximation compared to a more expensive one.
Any other questions? I know we're at time. We have a discussion portion after this, but just to be respectful of his time, maybe we could take one more question.
I feel free. It's okay. This is the end of my day too.
Thank you.
You're not curious to know how these GFlow-nets are going to make Bayesian calculations incredibly better? I don't know. This is my bet, but anyways, it would take more time to explain.
I was curious in that regard. Are you guys? I know we talked about this in the past at some point. Are you guys curious in the problem of applying it to just material discovery and not necessarily the adsorbate problem?
Sure. I mean, we would like to do all kinds of things have students thinking about the material design in general. Also, we have even more effort on the drug side of things for both small molecules and sequences, including 3D structure. But this is all very fresh. You can imagine the first paper on these methods is from a year ago. So we're still building up our expertise. Yep.
No, that sounds good. Yeah, I think that's one of the biggest challenges we're likely to face in the near future is when we talk about discovery and screening, using the existing known materials, you'll quickly deplete that set.
Yes, no, you want to be able to generate new ones. That's the key. So that's what I call, the imagination part. I think we can do some things to get off the ground with a list of given materials, but eventually, if you want to discover really powerful things, you have to open up to the whole space in some large family, of course.
Yep. Nope, makes sense.
And for that, we need chemists to tell us, like, where should we search? What are the boundaries of this exponentially large space?
Yep. Any other questions? If there are no other questions, thank you so much, Yoshua, for coming. Thank you for the great
Thanks for inviting me.
And
bye.
Looking forward to your work. Bye. All right, moving right along to our last part of the session is the discussion period. And this is really for everyone here. We really want to open it up for questions, for criticisms, for comments, for feedback, anything you guys have. We're all ears here, and this is our only second year doing this, and obviously we're learning from our past and hoping to kind of better the community moving forward. So we're really open to whatever people have to say. I'll open the floor to questions, or if anyone has anything specific.
To kick off some of the discussion, it was interesting to see the training times listed sort of in the thousands of hours of GPUs, and it looks like you have some very nice shiny new ones test. So is that a sort of reasonable level? Like, did you look at that and say that this was reasonable to do on the time scale of the competition, or an order of magnitude up or down would have been either more interesting or more feasible?
It was a lot of compute. I mean, and those aren't our GPUs. Like, that was a specific thing where we shelled out for cloud instances, because we have like shared computing resources for scaling some things. But in order to be able to get a reservation for like the amount of time or checkpoint, or just logistically, like for something that's this focused or this concentrated, cloud was just made so much more sense. So it was kind of a lot. It was, I mean, Elin, you'd be able to say much better than me, but I think compared to like our normal workflow, this was a special case.
Yes. Elin, actually, I have some question about the Equiformer. Since our team have also tried some sophisticated design on the transformer. Okay, some modifications, but from our point of the view, we found that it's very hard to beat the Graphformer performance. Okay, and so I want to ask that, have you tried incorporate the Equiformer with some, for example, the attention bias structure that's used in the Graphformer? Could this kind of thing will improve the performance or not?
I would say 3D Graphformer is, you can imagine that it is, I would say it's the type 0 version of Equiformer.
Okay.
Yeah, and because the interactions, I guess the only difference is that they use attention bias and share the attention for all the layers and then do the recycling. And I think that can definitely improve the performance. But I think for Equiformer, I keep it as simple as possible. I just build upon typical convolution, like convolutional neural network, like an equip, and then replace the convolution with graph attention. I think the implementation details matter, because I heavily tune the normalization layer and also activation function so that it works perfectly while being very simple.
Okay.
I hope that answers your question.
Okay. And I have another question to the OCP project. Okay. this is a very great data set, I think, because I have tried by ourselves to replicate the computation, the vast computation about the moleculars. And yes, actually, it takes a lot of the computation resources. And so I want to discuss about the roadmap about the OCP project. Could you plan to release more interesting data sets or tasks other than the OC12.2, the 22? Okay.
Larry, I'll give you that one.
Do you have any requests for specific things that you'd like us to release?
I'm not sure. Maybe the more the other kinds of DFT calculation scenarios other than the materials, maybe.
Yeah, it's likely
for
that we
example,
will. What's that?
The protons, the protons, some biological moleculars. Yeah.
So we probably will. Our team will probably not be releasing any data related to proteins, organics, that sort of thing, because it's outside of our personal scope. There is another team within FAIR that is working on proteins, but I don't think they have a plan on, running DFT or releasing data with regards to that. I would expect our team to release, every year or two, we try to release, another large data set. We'll likely release another data set this year, but it'll be on materials. It'll be for, something related to climate change, that sort of data. The other thing that we're looking into is, so far the data that we released, we basically, enumerate a ton of different materials, et cetera, and we just run full DFT calculations, on that, and then we just give everybody that data. In some ways, that's not a very efficient way of generating data, because a lot of the data that we generate is highly redundant. Like if you do a relaxation, 2 DFT calls, right after each other in that DFT relaxation are going to be, nearly the same training data. It's not going to add much to our ML models. So one thing we're considering doing is taking one of the ML models, running a bunch of relaxations with that over a greater diversity of materials, and then doing, single points here and there kind of randomly throughout those. So that way, all of the DFT calls we're doing aren't as redundant, as the ones that we're currently doing. And hopefully that'll give us greater diversity and, help train the ML models in the future. And one of the reasons for this is, if you look at the, force MEEs, we're not overfitting on that because there's tons of training data on those. But if you look at the energy MEEs, a lot of the best performing models are dramatically overfitting on the energies. I think because it just doesn't exist as much data from an energy perspective as our forces. So hoping that, maybe a sampling strategy like that might give us more data for less cost and improve the models.
Yeah.
And to add on to that, I think more recently, we released the Absorb ML paper, and there's an accompanying data set with that. And I don't think we emphasized it enough in the overview talk, but that
yes.
Yeah, I was going to say that data set is really the essence of the problem we're trying to tackle. Like OC20 helped us build these generalizable models, but what we really care about is how do we find this minimum binding site on the surface? So like this global optimization problem. Everything we're doing with IS2RE and OC20 has been really looking at the local region, but exploring that global optimization problem is really what catalysis researchers really care about, because that's the absorption energy that actually gets used. So that will be released hopefully early January, and the accompanying paper is already out there if people are interested. But we're hoping that one is a more interesting problem. It's really the next step of OC20, kind of the more downstream application that we hope others get excited about. And it's very likely it could be our next challenge for NeurIPS next year. So if you guys want to get a start, you can look at the paper now.
Okay.
But yeah, that is the case. We want to go downstream in our tasks. So, it's that computing the absorption energy and then potentially also linking that up with experimental results as well. So
yes.
Regarding materials, have you guys considered looking at things like, metal organic frameworks, other things that are, can be diversely used for different goals in curbing climate change?
Yes. Yeah, there's a good likelihood there might be some additional data in that space in the future. We're still figuring it out, and still kind of with each one of these, like the OC20 and OC22, it's an enormous amount of work. It's a lot, you're talking hundreds of millions of hours of compute. So you kind of have to get all your ducks in a row before you kind of pull the trigger on it. But we're working in directions such as those.
There was a question in the chat. How will we use the current trained models? I don't know, Brendan, just to mix the speakers up. Brendan, you want to give or someone else want to talk about how we're currently using it or practical applications of the current models?
I think you sort of answered it, honestly. Like I was going to chime in when you were saying that and just say you're kind of answering the question in the chat, because I think the Absorb ML paper is kind of, it's a downstream application. So we started by looking at, our force and energy MAE, and then you can kind of you can do the IS2RE task with a relaxation based approach. And then kind of the next step after that is trying to find the lowest energy binding site. So I think that's working our way farther and farther downstream.
Yep, absolutely. Larry, go ahead.
Yeah, I was just going to say, for those who aren't as knowledgeable on the chemistry side, once you find the lowest energy binding site, the absorption energy, that's typically correlated then with the experimental outcomes, like the reaction rates, ever potentials, etc. And that's one of the big questions we have is, are these computational quantities that we're estimating, will they be correlated, and how strongly will they be correlated? And that's one of the big questions we hope to tackle as a team, and we hope to kind of bring everybody along in that journey as well. By any data that we have in that space is then releasing that data to all you guys as well, so that way we can all explore that issue. Because maybe it's a simple correlation, it's simple linear regression, that sort of thing. Maybe it's more complex, and I think that's something that's going to be really interesting over the next year or so.
Will you be also open to proposal for simulating, either a new material or new configuration?
When you say simulating, do you mean computationally simulating, or do you mean experimentally simulating?
Yeah, well, I suppose experimentally will be a long way. Yes, numerically.
Well, this is actually a question. I'm not sure if it was one thing we've been debating as a team is basically opening up, allowing people to more easily do computational experiments, because not everybody is familiar to how to run the code base or has access to a lot of GPUs, etc. Is how useful would it be, for the community, for us to run a service or do something which allow people to, basically run relaxations without much knowledge of GPUs and etc. We probably won't open it up for people just to give us and actually do DFT calls, because as you know, like that's just really expensive. But I think the ML models, because they are so efficient, there is potential there that we could open it up for people to run the ML models, and then they could take the best looking ones and then do DFT on their side. I'm not sure if that would be useful to you or not, or if you're already running the ML models and it's more the DFT that you would like.
Well, I was thinking more of the DFT side. I mean, but also we probably need to vet, the type of experiment that makes sense, so that we're not just making simulation of random things.
Do you think the models already are quite helpful for making that process faster? And so my hope is that even these people doing very unrelated things, we found quite a few of the models you just train on OC20 are relatively transferable, especially if you're willing to do a little bit of additional DFT along the way. And so the best case scenario would be people like you or others are able to generate the data they need much faster than they would have been able to before. And again, it wasn't clear exactly how far the models were going to be able to go beyond inorganic surfaces, but I think the initial data does look pretty good that these should help a lot of other areas as well, because the models have seen the entire periodic table and organics and inorganics and those broad areas touch many, many different fields of material science and chemistry.
I had some notes here in case it got quiet. So I think it was nice. The invited talks hammered on all the points. And I got some high level just questions of where do we go from here as far as modeling is concerned. I'm sure everyone here is probably thinking about what do I work on next or where do I go from here. And the three things I had written down actually align with exactly what Yoshua and Gabor were talking about. And that were uncertainty estimation, active learning, and kind of equivariant models. Starting with the last one is, in the scope of OC20, we haven't seen like enough rigorous exploration of equivariant models and how rigorous, how well they do or how poor they do on our data sets. I know some of us are working in that field right now, but it will be interesting to see where that goes. I think people have shared interesting scaling laws regarding equivariant models. Physically, it's more natural and more meaningful as far as simulation is concerned, especially if people are interested in if we get to conservation of energy and how you make your forces. Or I think someone asked here about are we interested in running other simulations? And OC20 was like focused on relaxations, but molecular dynamics or transition state calculations are all super important. So looking into that will be something on our radar. But yeah, equivariant models still has a big question mark. Is this the gold standard for catalysis as well? Another thing was uncertainty estimation. I know Yoshua and Gabor talked about this. And as we move more and more downstream, as far as this kind of big picture open catalyst project is, at the end of the day, we want to make some prediction and tell some experimentalist, hey, can you synthesize this or some variant of it? And having no confidence or no notion of confidence in our models makes things a little difficult, because you could treat that as another screening method to inform more downstream applications. And lastly, active learning is most of OC20, OC22 were generated via like enumerating the search space, randomly sampling it. Larry talked about how redundant calculations can be. We have papers out there showing that if you train on 2 million, you can get nearly as good results as the 130 million data sets. So there's a lot of opportunities there of how can we systematically generate new data that can add meaningful information to the models and really push our models further. Of course, there's two axes to these, as you can continue improving metrics based off model architectures, but thinking about how do we leverage our resources to build more systematic data sets is something we can take advantage of. And we've just yet to explore that in depth to really curate these new data sets. I don't know if anyone has anything to add there, but just some thoughts, especially following the invited talks today.
Hello, I've got a question for the OCP team. Are you interested in any other intermediate, chemical quantities acquired from DFT calculations, like predicting the electron densities of the chemical system? Because actually, currently I'm working on a project of that specific task. So it would be very interesting if we can have, at least some data here in the catalyst system provided by the OCP team here. But I do believe that quantities like electron densities will add quite large overhead to the amount of the data here. But I think it has more potential to be applied to more tasks like predicting other quantities outside the relaxation energy here.
Yeah, I think that's a great point. And some of us have been thinking about that problem. We actually, I think a few months ago, released the Bader charge data set. So for all OC20 structures, we released Bader charge data. For those not familiar, it's kind of once you have this electronic density of your system, it kind of localizes the charge around an atom and gives per atom charges that are referred to beta chargers. I think there's more details there, but I won't dig into it. So we released that a while ago. If people were interested in leveraging that, we do have density data as far as like we ran our calculations, so we have all those outputs stored. We haven't released them just because I think the level of complexity, like starting really early on, we just want to make the problem really simple. The beta charge data was released a year later, but if people are interested in it, we have the data, it's sitting around. I mean, there's been numerous papers of people exploring how do you predict the density instead of energies or forces. And there's papers of how you can leverage the two models. But we just haven't, like, we released the beta charge data because someone asked, hey, can you release the data? Like they were interested in it. But if people are interested in it, I don't see any complications of releasing that. It would be interesting for people to explore.
We didn't release that because there was so much. I mean, the size of it was enormous, if I remember correctly.
Yeah, that's true.
So,
Yeah.
but we could do like a mini data set, or something like that. If,
I mean, I wonder if internally, like, if you're running all these calculations, if not to just make an ML model for yourself, just to initialize your charge densities from something that's a little bit better than maybe what VASP starts off with. I feel like you might be able to cut your compute in like a half or a tenth. But that's one use.
Yeah, I mean, the nice thing with VASP is the very first calculation is super expensive because you have this really poor density estimation, but all subsequent points are actually, like if you look at the inner loops, like the SCF calls, it's a lot less than the initial ones. So I think VASP naturally is doing that, but I think for future calculations, yeah, maybe giving it a better guess would be something interesting. And I think that's what people have been thinking about. Can we build models to better guess an initial starting point?
Yeah, I mean, will it be interesting that you kind of build up a platform and people can evaluate how their model, how the results predicted by their model can, I mean, by how many times boosting or reducing the simulation complexity on top of DFT. So I think that will also be some sort of meaningful quantity to evaluate the feasibility of the model.
Mm-hmm. Yep, absolutely.
On those lines, tying the charge density in with other developments, it's still interesting to me that none of the top models in the leaderboard have any sort of physics or Hamiltonian or electrostatics or anything else baked in. And so I would also just throw that out that it feels like a missed opportunity. I don't know how to do it, but it's a little surprising that none of the developments so far have been in that realm. And so I'm really interested to see how to tie those things together. Obviously, it's a hard problem.
Yeah, I feel like you kind of, again, run into this issue between wanting to do kind of customized operations and being able to fit something efficiently, like on a GPU, and also running it efficiently. And so I think we're not quite at the point where I can easily think of a model that maybe uses a good inductive bias and actually ensure that that'll execute efficiently enough to perform well on these types of data sets, because the current paradigms of these software frameworks, I mean, are completely excellent. I'm glad they very much exist, but they are catering towards different data. And that is hard to be. It is hard to be a really well optimized function. So I do think that's part of the trade-off and maybe why you're not seeing it. But I think in theory, like, yeah, I would also hope, I would hope that something like that would hopefully be more powerful,
I mean, to add on to that, I think Yoshua's slide had something about their recent model, like incorporating the period number, group number, all that stuff. I think in our experience, we've kind of explored that, and we've seen it not help. Like we've seen that these large data sets, you essentially learn that. So like given enough data, sometimes that stuff doesn't help. But like it does feel like in principle it should. It's just how do you do it correctly, given the scale of the data set?
Well, I think maybe at least my understanding of what Zach was getting at were things more of like not things like period number, like not like these kind of facts about elements, but more of something about the physical process or like screening. Like if you had some sort of notion of screening, or I don't know, Ewald something or something, that at least that was my understanding of what Zach was saying, but Zach, correct me.
Yeah, absolutely. And especially when you think about predicting charge density, right, then some of those things probably matter a little bit more, and it's a little bit more interesting than just even per atom energies or forces. And it feels like maybe you need something like that because the charge densities are very complex.
But then again, on the flip side, you also you have a lot of data in the charge density compared to a single energy, right? Like, so it'd be super interesting also just to see how much more quickly the model is able to learn. Because when you just give it an energy, I mean, that's pretty ambiguous. There's a lot of systems that'll have the same energy, but there's not that many systems that'll have the same charge density. So it'll be just really interesting to see the nature of how these models learn when given a much more rich data type to predict.
But I think the engineering challenges in doing so are very high. And it's I think it's we've talked about it a bunch, but once you start thinking about creating a grid, you know, over these cells and the density that you would need to do it, and there's a lot of creativity, I think, in thinking about how to do it computationally in a feasible manner. That, I mean, we're already blowing so much compute on all these problems. I'm like, this is it's a good way to 10x what we're currently doing, I guess. From a compute side.
Yeah, you very quickly run into like the classic problems of which basis set do you ally with,
Yeah.
We love local atomic orbitals, but we can't really beat the efficiency of plane wave calculations, and yet we're like, ooh, I really don't want to predict that many plane waves with my neural network. So yeah, kind of classic electronic structure problems.
So we are at time, but I just wanted to add, I had one question, just what can we do to help you guys? I think we're here, like, I mean, everything we do is open source and we're trying to better engage the community. I just wanted to make sure there was time to leave that question out there. If there's anything you wish, it could be as small as, oh, I don't like the way this is done in the repo, or anything more at a larger scale. If there's something on your mind that you wish you had, or a service you had or something, feel free to ask us. And if you don't want to bring it up here, we're all very open. You can feel free to message us, email us, post on the discussion board. But I did want to make sure this is a two-way street. We don't want to just drive the community in our direction. We do want to hear the feedback. Tess and Yelan, I see you guys were talking a lot. Did you guys have something?
Well, very selfishly, if you have any ideas for how to optimize a general equivariant tensor product, I mean, we would love that. Yeah, so that's all. That's very selfish request, but I'll make it anyway.
Brandon, I'll leave that one to you.
Yeah. How about anything related to the challenge? Is there anything like specifically about the challenge? I'm gonna act like a politician here and sidestep Tessa's question. But is there anything about the challenge that you guys would like to change potentially for next year, or anything that you'd like to see?
I think if we can have the more interesting downstream tasks, and I think this computation may be more attractive. And in my understanding, in the current level, we actually make the prediction of the energies, but this model is just application of the DFT calculations. And in my point of view, I cannot directly use this model to do the real material discovery. Yeah, in the current shape. So if we can build the more practical models or the applications for the computation. I think this will be meaningful both for the machine learning community and the material design, material discovery community. And we can really make a cross between these two communities and accelerate the both progress about the research, I think.
Yeah, absolutely. I think that's a great point. And I think everyone's eager to see, like everyone's eager, like, is OC20 really going to help the more downstream tasks? And while it may not seem like it now, just because we're so, I guess, a few levels up, we have been thinking about it. We have been exploring it, and you'd be surprised how well these models do despite their current performance. And that's, I think, with the recent Absorb ML, like, we get one step further downstream to thinking about how do we predict something that's actually practically useful. And it is, we haven't fully thought about what next year's challenge is going to be, but given that data set, given that people have thought about this, it could be the right time to kind of move more downstream as far as these applications are concerned. So that was great feedback. Thank you.
And yes, and I think from the model side, what is the threshold or the level that we can really use ML model for the material design or discovery? But for now, we say that the energy MAE about the 0.39 this level, and how much step we will make to make this model more is really applied for the real applications. I'm so curious about this one because I'm from the machine learning community and I don't know the requirements about the chemistry, the computational chemistry.
Yeah. Zach, you wanna answer that? You've been in the community for some time.
Yeah.
What is the milestone?
The standard answer you'll get is something like 0.1 EV is where people would like to be. But you want to be more accurate if you're trying to say, are two very similar things better or worse? So you can also imagine situations where 0.1 is not sufficient. One thing that's really interesting is that the numbers that are up on the leaderboard are for all the very, very diverse materials in OC20 and all of the complex intermediates that are in OC20. And a lot of catalysis is focused on actually much simpler problems than the very complicated things that we put into that data set. We did the data set the way it was because we wanted people to be very creative and build very generalizable force fields and really think about how to go outside of the box. But if you apply the current models to more standard things like simple metal surfaces and smaller descriptors, they're already doing better than 0.3. Those are the easier things to fit in OC20. And so I think the models as they are already quite useful for screening in that simpler space. I wouldn't trust them everywhere. I wouldn't trust them on the hard things. I would be careful about what you're doing. But in a lot of cases, it's closer to 0.2 or a little bit under. And that's enough to start saying, are some things, at least, do they have the possibility of being good or not? And to cut down the number of possibilities by quite a bit. So I don't think we are that far away in a lot of these spaces.
Okay.
Yeah.
It looks promising. I think we have the very near step to the milestone.
Actually connecting that with experiments and like some sort of large data set and really rigorously saying, how does that improve, right? That obviously is much more complicated, right? But the simpler near-term thing of just the computational catalysis screening, I think that's where there's already some benefit.
Do you have any specific analysis on, what specific type of system are particularly difficult to predict? Like to analyze the results of the models, like those summations on the server, to see, like the top 100 or 200 system out of the or test set, among which the models struggled in accurately predicting the quantities.
So obviously we can't release things from the test set or even say what are the hard ones. But for validation, we put a perspective up on ACS catalysis last year. It's also up on archive. And part of the perspective was on challenges and models, and part of it was also analyzing distributions among different compositions and different adsorbates. And so that's the one I would look at. If you have any trouble finding it, feel free to email any of us and we'll send you a link to it.
It's linked in the chat.
Excellent.
All right, any last questions? I know we're a bit over time.
I don't have a question, but just a comment. I just really wanted to thank the Open Catalysis project team for putting together this data set and as well as the challenge. So giving us a great opportunity to really test these methods and just giving us a good kind of focus of effort, a way to come together and kind of have a good competition. So thank you guys so much. I certainly know on my side, this has been a great opportunity. So thank you.
Thank you, thank you, thank you.
And always feel free to reach out. We're here for you guys. It's one of the big reasons we're doing this is, for the community. So thank you.
All right, if there's nothing else, all these talks will be on our YouTube page. You know where to find us, and we look forward to seeing you guys hopefully soon. Thank you.
Bye-bye.
Bye.
Bye-bye. Thank you.